Welcome back. So we were talking about truncated SVD, and we can truncate by choosing some value of r, we'll call it r prime, that is less than the value of r dictated by the singular value decomposition. And so we'll define our solution due to this truncated SVD in the same manner that we would for our regular least squares approach, except that now we're only going up to, we're doing the sum up to r prime. So we're going to pick up now and look at the error that comes due to this. We're going to have two types of error. One of those is going to be the error due to the fact that we have changed the SVD and therefore the inverse, and we no longer have this optimal solution that we spent so long developing using the pseudo inverse based on this SVD. Instead, we're going to have some approximation to that, but we'll also have less error growth due to large terms in our pseudo inverse. And so, you know, one's a benefit and one's a curse. Let's see how it balances out. So our truncated SVD is going to be a prime pseudo inverse times y, and then this is our old friend, this x hat p inverse is there we go. This is the pseudo inverse of a times the clean version of y. The clean version is the one without the error. Okay, so what we would like to see, our ideal error would be due to, or the very best case, no noise and full pseudo inverse is our p inverse. So we're seeing how far our truncated one is from this ideal case. Alright, so we have a prime dagger times y minus a prime times a times x. Okay, so this last one is because y in the clean case is just equal to ax. And so we can expand that out into a prime dagger ax plus a prime dagger e, and now minus a prime a x. Collecting terms, we get a prime dagger minus a dagger all times ax minus a prime dagger times e. So we'll deal with each of those terms separately. Let's grab this one first. And this will be equal to the sum from r equals r prime plus 1 to r minus 1 over sigma r. We have ax comma ur times VR. Okay. So now we're not sure what to do, so let's expand things out and see if any good comes of it. We here have j equals 1 to r. This is ax, and we know that ax can be written like this: x with vj times uj with ur vr. Now, one thing to note is that this and this are scalars, and we also know, so if these are scalars, we can pull everything out, and essentially now we just care about that inner product, and that inner product is going to be 0 everywhere except when j is equal to r. So we can get rid of the sum, and that's just r, that's r, and that's r. Just trying to save a few lines of writing here. Well, that's nice, because then sigma r and 1 over sigma r, they cancel. So when all is said and done, we're going to get the sum r prime plus 1 to capital R of negative. We're still going to have our x in there and its inner product with VR, and we still have the VR out to the right. So VR. Okay, now let's look at this second term right here, and we get that this is equal to, first, this is equal to, you know, we've got that negative out front. I don't want to lose track of it, so right now I'm just going to make it really clear that we're talking about a prime dagger e is equal to the sum r equals 1 to r prime 1 over sigma r e ur vr. Okay. Yeah, I don't know how that looks when I do it, but I paused the video for a sec because something didn't look right, and I was correct. The negative sign that I worked so hard to preserve on a prime dagger times e should actually be a plus sign. When I gathered the terms, I didn't keep track of the signs correctly, because that comes down like this. Okay, so there we are. So now we can look at combining all of these and seeing what our final error is. We would have x hat trunk minus x p inverse, remember that's the clean version, is equal to two terms. We're going to have a prime inverse times e, which is just, let's write this out, equal to the sum up to r prime 1 over sigma r e with ur vr. minus r equals r prime plus 1 to r x projected onto VR times VR. Okay, so this deserves a box. Not a red box because it's not quite that important, but it's very interesting. So let's describe what's going on here. This part right here is the noise error, and this part is the approximation error. But there's something really important here that enables us to do further and better analysis. That is that this and this, these two terms are mutually orthogonal. All the VRs, of course, they form an orthonormal basis, but we're in the first term we're going from 1 up to r prime, and in the second expression we're going from r prime plus 1 to r, so they're guaranteed to be different ones. That means that x, let's see, x hat trunc minus x p inverse hat squared, and this is just the Pythagorean theorem coming to help us out, is equal to our noise error squared plus the approximation error squared. Which is equal to the sum, once again using the Pythagorean theorem, which says that a squared sum is equal to the squares of the sums if they're orthogonal. We get x VR squared plus the sum r equals 1, oops, no, that's the E. R prime plus 1 to R like this. Okay, so this deserves a highlight. What is that saying? I think it's saying something your intuition was probably saying all along, and that is that the error introduced is going to be just, the error that we have is just the error, squared error due to our projection onto the noise, and that we also have additional error for all the terms of x that we ignored before. So let me copy this, and we'll go on and see if we can tease any other understanding out of it. on our next page. All right. And I think I left a term out. I sure did. This is we should have had 1 over sigma r squared right there. Double checking, that appears to be correct, so I'll fix that here too. Okay, well, what's going on here? Remember, we have, in addition to the fact that we are magnifying the noise based on 1 over sigma r squared, we also have the fact that this quantity here is maximized for E parallel, we use that symbol for a lot of things, parallel to VR, and so the whole quantity here let's do it this way. So this whole quantity is maximized for E parallel to V capital R, right? Because a capital R and the largest one there, so capital R prime, that's when sigma r is the smallest, and so if we've lined up our error in that direction, it's maximized. So and yet again, I did make a mistake. This is we're almost approaching the time to do things over stage. E is projected onto U, not V. As you saw before, and I copied incorrectly. Okay. So there we go. So we can look at the average error, and we'll do that in the next slide, or next lecture.